Okay, I'm going to share the screen. Okay. So this is welcome to the last topic of the semester, right? As you know, I mean, it is the last topic. If you know, next week, no class. And then the week after, I'll just finish up transformers. And if I have time, I'll do maybe another GAN example. And that's it. That's the semester. But these are the two generative models that we have available today in 2023, right? Generative adversarial networks, where the evolution takes us currently to stable diffusion models, and then, which is way more advanced, right? And then, but it starts with the idea of GANs. And then on the other end, the transformer, which is basically the algorithm that came out in 2017. So it literally, it's transformers. You can read through, I wrote these notes here. You can read a very detailed description of the transformer. Just go to that URL and you'll find that PDF, and then just read chapter 10, transformers. So obviously it's 100 pages. So I'll make the example that probably for the CNN, it took me at most 10 to 12 pages to describe the CNN in all detail and all the matrix multiplications. The transformer took me about 100 pages to describe it. It is just a lot of things going on, okay? So it's a complex algorithm, all right? So if you want a very detailed description of everything, read through this 100 pages, okay? Today, I'll just try to give you, I know, I mean, what do you want me to say? I'm sorry, it's just, it's just the reality of it. I spent the whole summer trying to understand how these things work, okay? So they're complex. And it's just because there's a lot of things going on, but in general, there's just like a couple of ideas, okay? So, yeah, so what I'll do today is I'll go over some of the description. I have some diagrams that should help to kind of understand how they work, hopefully. And then, of course, as you should know, transformers is the underlying architecture of ChatGPT, right? In ChatGPT, people can say whatever they want. It's a very powerful tool from OpenAI. But the architecture of the transformer really is just what this is. It's based on the original 2017 ideas, and it's not like it has evolved, into a more complex transformer. It's basically, it's very true to the original idea of the transformer, okay? So I'll just read this. I kind of wrote this back then, a few years ago. So you can see how it's dated a little bit, which I found it funny because it's up to a certain point in time. So transformers are the latest step in the evolution of deep learning. As is necessary with progress, newer deep learning algorithms are also much more complicated with deeper and more resource-intensive networks. Okay, the transformer is the best example of this. Transformers are, for me, and this is true, the first algorithm I was not able to run on my laptop. I just couldn't train with all the data, right? And all the memory requirements. They truly require a machine learning war machine, basically a GPU, right? So they do require that. Even the simple example I'm going to give you today, as I said, took me 10 minutes to train on my GPU. I have one RTX 2080, and it basically, that's how I was able to train it. So if you want this code to run, you're going to have to run it for a few hours, probably overnight, if you don't have a GPU, okay? The code that I'm going to give you, it's very much a continuation of what we've been doing all semester, object-oriented, but it is a lot more, even a lot more than the GAN, okay? So lots of GPU power and memory. The algorithms are much more complicated. And as you will see, the networks are, in fact, very deep. So this is where now deep learning is really deep learning. The architecture is very deep. So they were introduced in 2017, and they were made famous by the seminal paper, probably the most important AI paper in the last 30 years, probably since stochastic gradient descent, I would say, attention is all you need. Okay, that's the name of the paper. If you want to go read it, just Google it. It was authored by several people. The first author was Vaswani et al. And, that's the group. So now there's a couple of things. Before transformers, there was an algorithm. I'm sure a lot of you have heard of this one, RNNs, or recurrent neural networks. No doubt if you've ever been in deep learning, you've heard about RNNs. And then you might be saying, why aren't we covering RNNs in this class? Well, the reason why I decided to take out RNNs is that really transformers replace them for a lot of tasks. People still use RNNs and LSTMs, and I'm not saying you can't use them. The models can be used, but transformer, they were both tackling the same problem, which is like NLP types of things, generating text. And so transformers definitely took over. So the reason why I bring up RNNs is that they solve the classic example of the RNN, what is called the vanishing gradients problem. All right, so basically when you have a very deep neural network, right, you have matrix multiplications. And when you multiply two numbers like 0.5 times 0.4, the result is what? A smaller number. And then when you go to the next layer and you multiply 0.3 times 0.3, the resulting number is a smaller number. So you can see that eventually that number gets what? Really tiny, like 0 almost, right? And so what's the point of all weights being zeros? This problem is called the vanishing gradients. It's a very famous problem. And the transformers solve this also by using something called a residual. Now, some people might argue the residual has been added to RNNs too, sure. But the point is, they've solved this issue of the vanishing gradients in very deep neural networks. And that is, if anybody asks me what I think is like one of the developments that made true AI, true very intelligent AI possible, is solving that, the vanishing gradients problem. Because that means you can make really deep neural networks and things are not going to become all zeros. Does that make sense? So that was critical, okay? You wanted deep networks, but for a while you couldn't really get them because of that problem, okay? And so that was solved with a technique called residuals, and that was one of the many techniques in the transformer that makes it very successful. So as you can see here, it's kind of dated. So far, transformers have been used to develop very impressive implementations, to me at least, such as BERT and GPT-2. And obviously, this does not include Llama and ChatGPT and all of those, which are way more recent and have even surprised, many people. Like his name escapes me. Yeah, the computer guy, Jeffrey Hinton. Jeffrey Hinton has become surprised by them. All right, people that, all right, you think wouldn't get surprised. All right, so they're very good. Anyway, so I kind of wanted to just read that out because it's like a little bit of, giving you the perspective there. All right, so now I also want to mention, so here I mentioned BERT and GPT, right? ChatGPT gets its name from GPT. BERT, you may have heard BERT, Roberta, those are all based on the transformer architecture, but they're just different evolutions of it, if you want to think of it that way. So at the original Vaswani 2017 paper proposed a transformer, but the transformer is actually made up of two parts, an encoder and a decoder. And as it turns out, what happened in history is that some people decided, okay, the transformer is great, let's use it as is. Other people said, you know what, let's just use the decoder part. Let's decouple the encoder and the decoder parts of the transformer. Keep them exactly as they are, but just separate them so that now the transformer gave rise to three versions. The transformer that has an encoder and a decoder, that's one thing. It's used for certain things. That's the Vaswani paper. And then there's the encoder part used for a specific thing. And that's what gave rise to the BERT models. BERT, Roberta, Albert, all of those. And then there's the decoder. And the decoder is what gave rise to the GPTs. So the GPTs are decoders only, okay? So it's a little bit simplified. So the code that I will give you is only the decoder part. We're not going to do an encoder-decoder architecture. It's just much more complex. And I think just doing the decoder gets us to, getting a feel for it. Also, you might want to make your own chat GPT something, right? So from scratch. You only need 10,000 GPUs and all the internet, and $1 million probably or more. All right, anyway, so that's kind of the idea. So the original transformer didn't even have a name, like a fancy name like BERT or GPT. They just called it the encoder decoder with multi-head attention, okay? And that was really the idea. I think even the creators didn't know how powerful what they had created was going to be. I honestly believe it. All right, it was made by Google, I believe, so there's definitely that. Yeah, so, and then there's one trick in there called the attention mechanism. This is not an idea that was originated by them. In fact, a lot of the ideas of the transformer existed for a while, and they were coming from different areas, and then they just put everything together, right, and created this architecture called the encoder decoder with multi-head attention. All right, so let's take a look. So you can read through this. Basically, I go over all the details of everything. I wrote this in the old TensorFlow 1 approach, which allowed us to basically do all the matrix multiplications. So it's almost very close to like the math of how you would do it, okay? So it's not so abstracted as things are nowadays. All right, here is basically the first diagram that I will discuss, and it just kind of summarizes the whole thing, okay? This is the transformer as was proposed by Vaswani, basically, okay? So the best way to understand this is to understand why they created it like this. What were they trying to do? So the problem that they were tackling was actually language translation. All right, so they did this, their paper, I think, is written for the translation from English to Portuguese, okay? But that you can do this English to Spanish, English to German, English to any language that you can think of, okay? And so that was the idea. So you can see the big picture here, but let me see if I can I'm going to move this thing up. Okay. Then I'm going to do this. All right, so it's a little bit bigger so I can read it. So if you notice, this is the encoder, this part here, and this is the decoder, this part here, okay? So this is all a neural network. It's all vectors, okay? All vectors. So just like we do, if you get confused, think of MNIST, 784, right? It's a vector. So you get a vector here, you get a vector here, you get vectors everywhere in between. So you can think of it as a whole bunch of neural networks that have an input, a vector, and the output is another vector. And then that output becomes the input of the next layer, okay? So this is the encoder. It's made up of the input, which you can basically think of it as, I'm going to ground it in the problem of language translation, okay? So we're going to translate from English to Portuguese. One problem with languages is what? In English, you might say the blue car. But in other languages, you might say the car blue. That's a problem, that things don't translate in order. Or in some languages like Turkish, you may have like 30 words or something, and in English you have 10. So they're bigger, more syllables, whatever it is. So this was the problem that people were trying to solve for many years, right? That ordering, the size, etc. Okay. So the transformer then takes in the English sentence, and it basically does some steps to convert, and that needs to be received as a vector. So we'll talk about that a little bit. Okay, that vector of the English sentence needs to go into another layer, which does something called the embeddings. So what that means is that every word is going to be represented by vectors of a specific size. You pick the size. So let's say that you say every word is going to be a vector of size 784. But what are the values? You don't know what those values are. In fact, you initialize that randomly, and as you're training the neural network, those will get filled in. Okay, so that's the basic idea. You do have to select the vocabulary first, and we'll talk a little bit about that. But for now, for the sake of argument, let's say that you just pick 70,000 English words. Okay, and those words will have not the word itself, but an ID. So the will be 3, cat is 17, xylophone is probably 65,000 something in the ID. So they are ordering by frequency, how often they appear in the alphabet, in the vocabulary, in the language. And you don't drop words like the, for instance. You keep them in there because you want to have good grammar. This is why ChatGPT has good grammar, right? Because it knows where the goes. Okay, got it? Now, one interesting thing is that when you go from this English sentence, I'm just doing a high overview right now, okay? So when you go from the English sentence, you give the whole sentence all at once, right? But you need to do what is called the positional encoding. And the positional encoding just means that you have a vector of all the words, and that vector will tell you which words, you have an additional vector of the encoding of the position so that you know, okay, this word appears first, this word is second, this word is third. So you have a vector of the order of the words, okay? So you give it the sentence, that cat is sleeping on the table. You give it that, and then that's going to be converted into, let's say that's, and also another thing is that you want to give it multiple sentences, right? So sometimes you'll give it the cat is sleeping on the bed. Another time you'll say the cat ate the food. Another time the cat fought with another cat and one beat the other and then the cats died. Longer, shorter, right? So you have all these different sizes of sentences. So how do you handle that problem, do you think? The simple solution with the transformer is just to say all sentences are going to be represented by vectors of size 40. That means that I allow 40 words. Did I start this thing? I did, right? Yeah. Okay, so you're gonna say that all sentences are of size 40. If a sentence is shorter than 40, what do? You just put zeros at the end. You pad it. If the sentence is larger than 40 words, what do? You truncate it. So you lose some information. So obviously pick a good size, right? A good size that is, large, right? So the sentence is a vector of size 40 where you put the IDs. Yeah. So you create a vocabulary, let's say 70,000 English words. Okay. So the is always 3. Okay. Cat is always 17. Xylophone is always 65,000. Yeah. But those IDs cannot go into the transformer. The transformer doesn't know what to do with them. Right. So what it does is, you can see now that this becomes, over here, you can see a vector of 40 by 512. Okay. So what does that mean? 40 IDs by 512. So every ID is a vector of 512. Do you see that? Does that make sense, guys?
So we have 40 words, vectors by 512. If you don't hit 512,
No. It's 40 is the number of words in the sentence. That's the number of words. So the cat is sleeping on the table. That's like 7 words, 7 IDs. The rest are padded and ignored. Yeah, 0, let's say. That's the 40. The 512 is the representation of each word as an embedded vector.
Oh, okay.
Okay, so we don't, if you give the 3 ID to the transformer, that's meaningless to it. Or you give it 17, it's meaningless to it. What it needs to know is that 17 is a vector of 512, and 3 is a vector of 512, and 65,000 is a vector of 512. Why? Why is that important? Because those vectors of 512 are going to have values, right, that represent something about the word. Okay, that's how you do it. Okay, so the information about the word is in these embeddings of size 512. This is an idea that comes from Word2Vec and all of those models, right? Where you have an embedding representation of an embedding, which is basically a representation of the words. So for instance, just to give you like an exaggerated example, right? Let's say that you have a vector of 512. So that means you have a space of 512, right? 512 axis. But to keep it simple, let's say 3. So we can visualize it, right? Cat, dog, and bear. So the axis, this axis represents furriness. You see that? So what do cats, dogs, and bears have in common? They have fur. So the value, if this is 0 and that's a 1, where you see that pillar there, that's the value that they get for that column. You see that? Very furry. Then, so that's cat, dog, and bear. Xylophone does not have fur, so the value is like maybe down here for this axis because it's not furry. So what the embedding is doing is it's telling you something about the words, like furriness or lack thereof, and other properties like musicalness. So then maybe musicalness is that axis. You see that? So what do cats, dogs, and bears? They're not very musical, probably. So it's a lower value, right? On this axis, sorry, on this axis is a lower, but xylophone is higher. Do you see that? So then you could say that the words bear, cat, and dog appear over there. Xylophone appears over there. Do you see the intuition? Yes, sir.
So it's gonna be 512 axis, right?
Yes, axis. So remember, you're thinking about whenever you have a vector, right? That represents all your samples, that's a vector space. So for instance, when we did MNIST, right, we had 60,000 images, but they're all of size 784, right? So each one of those represents an axis. So it's they're all orthogonal, which means they're all 90 degrees from each other. Now, humans can only picture 3 dimensions, but mathematically, we can have vector spaces that have an infinite size. Did I answer your question?
Yeah.
Yeah. All right. So this is an important intuition. Okay. This is the standard. Yeah. Go ahead.
So how are we determining that?
Those values
Yeah.
of the embeddings. Yeah, that's a good one. So there's a 2-step process. The first step is to determine what the vocabulary will be. Let's say I just picked 70,000. I made it super easy, but you have better ways of doing that. And then you just create the n just means the number of batches, because remember that you're actually training in batches, right? So you're giving it not just 1 English, 1 Portuguese, but let's say 64 English and Portuguese samples. That's a batch. You guys know what I mean, right? Right? That's what the n. The 40 by 512 just means the sentence, right? The 40 is the words, the IDs, and the 512 is the vector for each one. Initially, those values are random. And as you remember, the transformers need tons of data to be trained, right? So I once trained a transformer for English to Spanish translation. It took me 2 million pairs of English to Spanish sentences. As you are training this, the embeddings are being learned. So the transformer learns the embeddings. So it's not like Word2Vec, where you have like a list of all the words and embeddings. The transformer does not work like that. The transformer, in fact, changes the embeddings based on what it's getting. So it's an embedding machine. It really is an embedding machine. Yeah, go ahead.
So how are we like determining that we should like take 512?
That's architecture. But usually it's limited by your RAM. So 784, I think, is what I have tried. And I think if you have very powerful computer, I don't know, ChatGPT might be 2048 or 40 something. So it's just obviously you're right? I think you're thinking and saying the bigger the embedding, the better quality possibly. And you're right to think that way, but there's a constraint, and that is the computer that you have, RAM, GPU. So this is why I said to train ChatGPT is 10,000 GPUs. but also you're training it with the whole internet. Think about this. It's like me saying I'm going to give it every possible English and Portuguese pair that conceivable and train this model. You see that? So it actually learns these embeddings inside the machinery, and they're there. There's no way of extracting them exactly because they're just weights that are, you give it inputs and it gives you an embedding at some point. You guys see what I'm saying? Any questions? All right. Think about this, right? We've only covered these two things, and we've spent all this time. So this is the transformer. This is only the encoder, right? So you give it the English sentence. Obviously, over here you would give it the Portuguese sentence, but we'll talk about that. Then you do the embedding structure, and then that embedding. Notice this is already like a cube, right? So it's n by 40 by 512. So it's number of batches by 40 tokens for each sentence. Some padded, some truncated. 512 is the embedding size. And then that goes into this orange section. The orange section is basically the encoder architecture. The encoder architecture is made up of for the original paper, made up of 1, 2, 3, 4, 5, 6 encoder layers. They're all the same. It basically has 6 of these. This is why now object-oriented programming is really great, because you only have to create the encoder layer class, and then you instantiate it 6 times. You see that? You see how it starts to make sense, and it makes your coding easier. Okay? So what's going to happen here? In its simplest form, we give it this vector, n40 by 512. It goes into this layer, and we get out of it a layer, we get an output that is n by 40 by 512. And then that becomes the input to the next one, and that, once again, it's gonna produce an n40 by 512 and so on. So what are you doing? You're transforming. You see that? You see what's going on? So the question is, what is happening in these encoder layers, right? That's what you probably want to know. So I have a diagram for the encoder layer. We'll talk about that in a second. But in its simplest form, what are we doing? We have an input, a neural network, right? So what do? Think of this as X. We got W, so X times W, and that produces the next one. And then that becomes the input to the next one and the next one. Okay? There is one thing in all of these layers called the attention mechanism. And so that's one thing that I'll mention a little bit later. Right? So for now, let's just think of the overall architecture, and then we can drill down into each of these. Got it? So think of it as we get n40 by 512, it goes through here, and we get n40 by 512. All that's happening inside these layers is that as neural networks work, take an X times a W and produces a Y, okay, plus biases. Okay, is that clear? All right, so that's going to happen in 6 layers, okay? And after this, this is all neural networks, so very deep. And then at the end, guess what you get? n40 by 512. All right, now that's the encoding. What comes out of here is not meaningful to a human. You don't know. It's just that cube, let's say, with values, okay? You basically encoded the English sentence into that. Okay? And then what happens now, if you notice, the encoder output would move, and it goes into all the decoder layers of the decoder of the transformer. Okay? You need that information, right? Because you're doing language translation. Okay? So now let's look at this part over here. Now we have to think about this different. We have to know if we're training or if we're testing. If we're training, we're going to take an approach, and if we're testing, we take a different approach, or doing inference. Okay, but this is what is called an autoregressive model. So basically, what that means is this is basically predicting an output. So this is the GPT part, right? So if I say the car is going, really, you guys are a GPT because you know exactly what word to say, don't you? Lenny, the car is going really fast, right? David, or slow. But you're not going to say the car is going really hamburger, right? You see that? You're a GPT, you're a GPT. So what's happening is in the GPT, in the decoder part, is that think of it like this. You say the. It learned about cars and vehicles that go fast, right? So because of that, the next thing is some noun, some machine that goes really fast. So the GPT will say the boat. Those two tokens, right? The boat goes back. It's auto-regressive. So it's the output and now becomes part of the input again. So now what do you say? The boat is the input down here. You see that? Goes through the decoder. So what does the output of the decoder have to be now? It's just going to be the boat is. You see that? And then that is input again. So the boat is goes through the network, and now the output should be the boat is going. You see that? That's an autoregressive model. So basically, a simple way of thinking about this is that you are giving it the Portuguese sentence as input and as output, because it is producing Portuguese. No? Right? You guys see what I'm saying? It's producing the boat is going in Portuguese on this example. But you also need to know, because you're translating the English, right? So you give it the English part here, and that goes into the decoders over here. So that's the original Vaswani architecture, okay? So to train, you would give it the English, and you would give it the Portuguese here, okay? And over here, you would give it the same Portuguese sentence that you gave it down here, except that they were shifted by one word to account for the auto-regressiveness. You see what I'm saying? So it would say, the boat is, and up there, it would say the boat is going. So why is that? Because when you're training, you need to know what the actual word should be. So when you're training, what do? The boat is, right? You give it as input, and the model predicts the boat is hamburger. It's going to compare that to the shifted true version, the boat is going. Does that make sense? That's how the training process works. So you give it English sentence here, the translated Portuguese sentence here, except that they are shifted, as you're always trained during the training process. So that way it gets the English information that it needs, and it knows, okay, what's the next word that I need to predict of the Portuguese? Got it? Okay, so English here, Portuguese here, and Portuguese over here. This took me a while to understand, actually. Yeah, go ahead. Yeah, go ahead, please.
So the blue line coming out of the encoder output, and then each arrow going into the different decoder layers?
Yes.
Is that like first encoder layer going into that first decoder layer?
No, it's the output of the whole encoder.
Okay.
Yep. It's the out, because you assume that it's almost like the brain. You have like more brain. You know what I mean? You give it more layers, there's more brain in there, more neural networks, more attention mechanisms paying attention to things. Not just to the original tokens, but actually to the outputs of layers, where hopefully you have more meaning going on in them. Yeah, please. Yeah.
So is each one of those layers?
Which layers? The encoder layers?
Yeah, either. Are any of those considered the attention heads?
The attentions are inside.
Okay, inside each encoder layer.
Yes. We're zoomed out. We have to zoom in into these. The residual is in there, the attention is in all of these, and we have to pay attention to these things. Got it? All right. So yeah, good question. So anyway, so that currently I just want you to visualize, right? You're translating, so this is English, this is Portuguese, this is also Portuguese, but it is the shifted Portuguese, right? So that you can actually remember that in training, what do you always do? You get an input, you predict, and you compare the predicted to the real, right? And so you need to measure the performance that way, the loss, because you want to minimize it. Okay? So if you give it English and it goes through here, you give it Portuguese and it's the boat is going really, and then here it says hamburger, but the real sentence is the boat is going really fast, then what does that mean? The loss is bad, right? So you need to update the weights in another way so that the next time around you give it English and you say the boat is going really, and it says not hamburger, but fast or slow. Okay, that's how you adjust the weights. It's the same mechanism. That's during training. That's called teacher forcing, is the technique. When you're doing prediction, obviously it doesn't work that way. When you're doing prediction, but at this point, you've already trained the model also, right? So then you would give it and as I said, then it's going to say boat. So then it's going to be the boat is going, and so on. And that's the autoregressiveness, and this is why GPT can do things, okay? Now, keep in mind, GPT as is would only say gibberish. It sounds grammatical and very real, but it's just saying whatever, okay? You have to do additional things in order for it to start answering about a topic, okay? And that's kind of outside of this. This is just, so I'll show you the example I have with Tiny Shakespeare. It just says Shakespearean babbling. Okay, that's pretty much what it's doing. But that's exactly how it works. Okay, is this clear, guys? All right, go ahead. Why is there a linear layer? Very, very good observation, right? So good question. So here you give it the sentence, you encode it, you give it the Portuguese sentence, you encode it. But here, after this layer, this is just a regular feed-forward layer, okay? And what you get out of here is an n by 40 by vocabulary size. So think about that. What is it doing now? For those 40 is going to predict what? A vector of vocabulary size, which was what? 70,000, right? And what does it predict there? All are 0 except one of them which will have a 1. And what does that translate to? Not but the predicted word. Because remember, our vocabulary had 70,000 words, and actually there's Portuguese words and there's English words, obviously, right? So it's gonna say, that's why your question is pretty good, right? We use this linear layer just to kind of go from the encodings to the final layer, which should produce for every one of the 40, the word that we're predicting. So remember, for instance, in Turkish, you say something in English, 10 words, Turkish may have 30 words. So you need a vector of 40 to produce those 30 words. But here is where you actually predict the ID. You no longer need the embeddings. You don't want them anymore. You actually just want ID 3, which was the, ID 17, which was bird, ID 65,000, which was xylophone. You see what I'm saying? So this is how it produces the words. Is that clear, guys? That was a good question. So any other questions? All right, so this is the overall idea of the transformer. Okay, so remember, it was done for language translation, basically. Then now let's think about BERT a little bit. I'll have a little bit of a quick lecture on BERT next week, but basically the idea with BERT is this. You decouple it, right? So you don't have a decoder anymore. And I actually think it's easier to understand just an encoder or just a decoder separate. So the encoder is, you give it the English sentence, forget about Portuguese, and what does it produce? a 40 by, let's say the batch is only one, there's only one sentence, right? So I give it the sentence, the house is on fire and the fire truck arrived and saved everyone. Okay, so you give it that sentence. That comes out as a vector of 1 by 40 by 512, an embedding. You don't know what it is per se, but it's an embedding. It's something useful that you can use, right? And then what the BERT models do is they basically take this thing, this layer here, and tack it on over here. So that you can infer now, pretty much as we did it here, the words. But what words does it actually, so how does it train, you might say? The way that it trains is you give it English sentence and you give it the exact same English sentence at the end. Why is that useful, you might ask? Well, here's the trick. Remember fill in the blank? You've been doing that type of exam since you were in elementary school, right? Fill in the blank. You know, the inference function is used in machine learning, right? So this is how you train a BERT model. You give it English, but randomly you blank out some words. So what does this transformer learn how to do? It learns how to take a sentence as input and guess what the missing words should be. It predicts those words and then it compares them to what it has already, right? Because it's the same sentence. Do you guys see that? Does that make sense? That's what BERT models do. So all they did is they took the encoder, added this layer, and now the training process is give it the car is going really fast. And over here you say the is going really fast. So the transformer guesses motorcycle and it gets it wrong. It guesses mountain and it gets it really wrong. It guesses car and it gets it wrong. Do you see what I'm saying? And now this encoder can do that. Okay, once you've done that, then you can remove the words and add other things that you wanted to predict. So they add like other functionality that they want to add to it. But you have a transformer that in essence knows what words are missing. Okay, that's just that's how the BERT models work. Any questions on that? Nope. All right, and then the GPT models, as I said, decouple, forget about the encoder, just go with the decoder now. Okay, so what's going to happen is you want a parrot. Just talk. Say whatever. I say the volcano is about to, and then it's going to say it's going to explode, and then some reason why, because it read it on Wikipedia, and that's what GPTs do. So when you train a GPT, think about it. You give it all of Wikipedia, for instance, right? You're going to give it the sentence, right? Whatever the sentence is, as input, and the same sentence as output, except shifted by one word. So you do the shifting. Remember at the beginning of the semester, one of the problems I gave you was to shift vectors. I asked you in the NumPy, shift a vector by one. This is why I asked you to do it. That exact same operation is what's happening here. You just shifted by one. Why? Because it has to learn that given the words that I have already in this order, what's the next word? Okay, and by having them shifted, you have the real label data, right? And so the model predicts and you compare to the real, and this is how you update the weights. Got it? All right, great. All right, so anyway, that's kind of the big picture of encoders of the transformer in itself. Okay, if you notice, I separated this as transformer and inputs during testing and transformers and input during training, okay? Because there's basically a difference of how the architectures work, okay? So notice that really the difference is in the testing that it's this arrow, right? You see this blue arrow? Because now in the testing, it predicts a word and that becomes part of the input. And I've said it, that's called an autoregressive model, okay? In the training, the arrow is not there but you don't need it because you have the sentences just shifted by one. Got it? So there's a difference between training and testing. Okay. All right, so that's the overall architecture. The main ideas of the transformer are, I have them listed here. You can read through this, so it's got all the details, actually, of everything I've said is pretty much here with examples, like the padding thing. Talked about that. Now, there's this idea of masks. So this is an important concept also in the NumPy examples. I asked you to do some masks, remember? So why do you do that? Well, for the simple case of blanking out the next word. Do you see that? So you always give it the full sentence, right? Let's say, right? But you want to decide how much of it you mask so that you don't, so it just simplifies the code, because the mask, if you didn't have the mask, you would have to like keep track of where you are and only look up to here. Whereas if you have a mask, you do the matrix multiplication and then finally times the mask, so that it only shows the parts that you want to show. Do you see that? That's what the mask does. It's just a very efficient way by doing a matrix multiplication of blanking out some of the words, so it doesn't see them sometimes. Okay, and that's just, again, because since you're doing the transformer was actually like almost like designed for a GPU. It was designed in that idea. Remember that the GPU is basically matrix multiplications. That's what it does, right? And so the code needs to be like that in order to be efficient. Teacher forcing is that idea of shifting the things that I already discussed. So that's one of the ideas. Attention. So the attention mechanism, I'll read through it for now, is key, right? Now, this was invented before. The attention was, and they just implemented it into the transformer. The attention mechanism in transformers is the heart of the whole algorithm. Okay, is key. The attention matrix is nothing more than a dot product matrix multiplication between all the words in a sentence. So for instance, the English sentence. The idea is that given the input and output, the model learns to correlate the words in the sentence to determine their importance. And this is done multiple times, and that is why it is called a multi-head attention mechanism. Right? So the idea is like, the embedding of the word bank. This is probably the best example I can give. The embedding of the word bank, right? So we have Bank of the River, the bank where my money is, and maybe some other bank, I don't know. But let's just take those two, right? So if I say the bank, the people were walking and they slipped on the bank of the river, right? So if you create a matrix of that sentence by that sentence, right? You're like a correlation matrix. Then the words bank and river should be what? Should have like an indication between them, like bank and river, that there's a high correlation there. You see what I'm saying? But if I say, I put all my money in the bank next to the river. That's a good example I just thought of. All right, so now when I correlate these words, bank and my money are highly correlated. Bank and river should have a low correlation, because the bank form or tense that I'm talking about is the building, right? The building structure which relates to money, not the sandy thing next to a river. You see what I'm saying? So that's what the attention mechanism is doing, is that it's taking the sentences as they go in. So here's a good example. What was the size of our input? 40. Padded or truncated is 40. So what does the attention matrix look like then? What's the size of it? Always 40 by 40. Do you see that? 40 by 40. Put all the words and the same words over here, but based on the context, the transformer will learn. Do they mean bank, the sandy thing next to a river, or do they mean bank, the building that has money. How do you understand that when you speak your language? You understand it by the context. So you say, the bank has my money and the robbers rob the money. Okay, so money and bank highly correlated, and then they drown in the river. River is not really relevant to this form of bank. You see that? And that tells you a lot, because now before, a good example of this is before, in the past, if I had the word bank, it would have been the same embedding, for instance. How would you tell the difference? You see that? But now you can create an embedding for bank based on the words around it. And that's really powerful. You guys see that? Does that make sense? That's what the attention mechanism does, okay? So it's like you have this matrix multiplication that is happening, and that's adjusting the weight so that by highlighting bank and river or bank and cash, each one of those will produce a different embedding of size 512. One which is more bankiness and one that is more riverness, if you will. Got it? So that's the attention mechanism, really. I mean, there's more, it's like additional things in the math, but in general, that's the overall idea. Questions?
So let's say the topic of the banks, instead it relates to money and.
Well, remember, Lenny, that each word should have an embedding of size 512. But the machine learning algorithm, the transformer, learns what those values should be. If you didn't have attention, it would always say the same values, whether it's bank of the river or bank where you have your cash. What's the problem with that? Then the transformer is not very good, because it really can't differentiate between if you're being a building or you mean a sandy area. Do you see that?
Yeah.
Attention gives you this power now, where if I read, as I said, the money is in the bank, and then the next time is the robbers assaulted the bank and took the cash, and then it reads a whole bunch of news articles about the stock market and the bank, and it's learning that bank relates to financial things. That's an embedding. And other many thousands or millions of articles, it reads, we were walking next to the river on the bank of the river, right? You see, people slipped on the bank of the river. The bank of the river is going to get an upgrade next year. They're investing. All of these things are teaching the transformer that whenever bank and money is one thing, bank and sandy area is another thing, and that's really, it's learning to differentiate. It almost, you could say it's understanding. I mean, maybe. This is why a lot of people just don't quite know where to draw the line of what is understanding, actually, right? What is the transformer actually doing? And it's doing it in 6 layers, right? So there's not just one attention, but there's 6 of them. Do you guys see that? Making sense? All right. Embeddings, I already talked about that, right? So we discussed this, so that's another idea. The positional encoding, we talked about that, right? How do we indicate that the came first and the bird, and that's done in that basically it's important because everything is done in parallel. Everything is done, a matrix multiplication. So you need to encode that in an efficient way, okay? For the matrix multiplications in the GPU. Okay, so this just goes into the code and breaks it down. I do have some additional graphs in here. I'm looking for them. I mean, I recommend you read everything. Okay, I think this is the layers. So the encoder layer. So this would be in the whole encoder, we had 6 layers, right? And so this should be a diagram of the encoder layer somewhere in here. Yeah, there it is. So notice, what is it basically? You have your 40 by 512, right? Remember, the N is just a batch. So it could be 1, 32, 16, whatever you want. You can almost forget about it and just think it's 1. And so it's just 40 by 512. And the output is always 40 by 512, but it's an embedding. And what does it do? It goes into the multi-head attention layer, which is basically I just described. Why is it multi-head? I actually have the code in here for that. So these are the 6 encoder layers, right? And then I think it's probably in the next one then. So these are the 6 encoder layers. And basically you can see if like encoder layer, you have the initial vector, that becomes H1, and guess what? H1 becomes the input of the next one, which produces H2, and that becomes, and so on. Okay, you see that? That's the 6 layers. So you can take a look at that code. But basically the encoder layer then, you have your N by 40 by 512, that goes into the multi-head attention layer, and you get a matrix multiplication there, right? Your 40 by 40. And then notice after the output of that, fully connected layer. The standard hidden layer that you guys know already. The size of that, I can't remember what it is. We can look at it, but you can change it, obviously. And then that should produce a 40 by 512. So you have to make sure that when you do the matrix multiplications, they produce an N by 40 by 512, which you'll see it's in the code. Okay, that's just linear algebra, getting that right. Okay. There it is. This is why it's multi-head attention. The multi-head attention is here. Notice this code here, this function is just one encoder layer of the 6, right? It's got the little thing, the X and the mask, right, that I mentioned. And then notice here, what do? Notice that is X, 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 X. So it's all the X's. I think there's 8 in there. And each one of those inputs goes into the attention mechanism to produce its own version. So the best way that I can describe this is like this. I give it, the car is going really fast, right? And that goes into one attention layer. And then in the second one, the car is going really fast, goes into the attention layer. But another attention. And then the same sentence goes into another. So you basically send the sentence into 8 different attention layers. The same sentence. Yes. Why do you do that? With the hope that it's gonna learn different things. Do you see that? So sometimes it pays attention to this, sometimes it pays attention to that. Because it could be that the bank of the river was very slippery. The bank had money that was robbed. There was a river next to the bank. You know what I mean? So it's like it's more ambiguous, right? And so what you want to have is by having other layers, it pays attention to different things. So you just give it more power, more compute power. Got it? So, I mean, if you get confused sometimes of why, just go down to the code and look at the math. The math says the same input X, the architecture of multi-head, and that should produce a C1. However, those weights are learned differently because it might be paying attention to different things, okay? Then what happens here is you have these C1s, and these C1s, notice, you have to look at the function here, but they're actually coming out smaller. Okay, they're coming out smaller, and in that step, they get concatenated. Concatenated, yeah. So it's like a vector. So the vector was originally, I think, 512, right? What is 64 times 8? 512, oh, nice. So what does that mean, basically? These are just like the tricks they do. Give it the sentence, pay attention to it, produces a vector of 512, shrink it to 64, you produce 8 of those, concatenate it, you're back at a vector of size 512. Do you guys see that? Don't ask me why they did that, but it works, right? So this is what I was saying. This is the genius of the things. How did they think of this? I don't know exactly. And it makes sense to me that it probably, they wanted to pay attention 8 times, hopefully in different ways. But then you had 8 times 512. That's kind of big. And they just said it's too big, it's going to make it inefficient. Well, let's just make it smaller, 64. Let's go back to our 512. Let's see if it works. It works really well. And you can play with these ideas. You see, you can extend it a little bit more, but that's, I would say that's actually probably how it works. Got it? Does that make sense? Yeah. Yeah, this is, yeah, in one encoder layer. Yeah. So remember, follow the code. Initially here, I have 6 encoder layers where one feeds into the next one and the next one. But in each encoder layer, I have 8 attentions. So I give it the input X 8 times to these attention layers, and it produces C1, C2, all the way to C8. Except that they're not 512 anymore, they're 64. But 64 times 8 is 512, so you just concatenate them and end up with the vector. Remember that at the end of the day, you're doing all of this and you need to produce a word and you're going to compare it to the real one. If it's not good, change the weights. If it's not good again, change the weights. Eventually, you get the word that you want. That's a good set of weights. Got it? Yeah. All right. So that's it. That's the encoder layer. This got some more steps in there. And then that's the encoder multi-head. We talked about that. The residual. This is actually important. So the residual is what I said, takes care of the vanishing gradients problem, right? So notice what the residual is here is basically you give it X, it produces C, right? So you could argue that C is the product of what? Of multiplying X times some weights, so the numbers would vanish eventually. You see what I'm saying? Because the multiplication starts producing smaller and smaller and smaller numbers. How did they solve it? X plus C. Remember, C is a result of running X times the weights to produce. So what you do is you leave the X. It almost like it flows. It's like goes in and it comes out plus the C. And this is called a residual. It's a technique, basically. So the unaltered values make it to the next level, but plus C. And C is the X going into some multiplications to produce it. That's the residual. Sounds crazy, but that solves the problem, basically. Okay. All right, and then so I think that's basically all the ideas. I mean, all of this is just like very details of the transformer, but we'll go over this in the code. Yeah, congratulations. There you go. So we're done. And then the decoder has a similar architecture. Okay. So the decoder has a similar architecture, except what's the difference in the decoder layer? The encoded vector, right? So the output of the encoder is this one. Remember this? So in an encoder, you had 512, a multi-head attention, which we have discussed, and a fully connected layer, right? We didn't need an input, something to handle another vector. But now in the decoder layer, we do need it. Okay? And so that's what this is for. So this is the same. The 40 by 512 goes into the multi-head and produces this output. But now you also have the encoder 40 by 512. Both of them go into a structure called the encoder decoder attention layer. Okay. And then that goes into a fully connected, it produces the 512. Similar idea. Okay? All right. So that's basically the overall picture of this. My suggestion is read through this. As I said, the transformer is a pretty complex architecture. Let's see if I have anything else worth mentioning. Yes, we talked about that. I've mentioned this already. Right, so this is just this part, I have an example here of kind of what the GPT is doing, right? So if you think, you give it just a decoder, right? You give it SOS, which in this case would be a token that just means what? Start of sentence. And then what does it do? It predicts A. You see that? Then this A becomes the input in the next iteration, so it's SOS A. So it predicts lion, right? And then lion becomes part of the input, so it's SOS A lion predicts in. So SOS a lion in the, and so on. Okay, so this is an example of what I was saying with the decoder part. Once, not during training, because during training you just give it the sentence shifted and masked, right? But once it's predicting, this is the behavior that it should have. Okay, and this is why ChatGPT can just speak and say things. Okay, and it's very grammatical, but it's making up everything it's saying. It's literally lying. It's true, right? Because it doesn't know. It doesn't know. I mean, it just the kingdom of, and it's gonna say, oh, the kingdom of the king, and there's a queen, and it's gonna make up stuff. All right, so this, I think, the rest I leave it to you guys to just read through because there's a lot of details, as I said. But I think I touched on the major ideas. So now we're gonna, in the time that we have left, we're gonna shift to the code, because I do have some code, and then we're gonna finish that up next week or next time we meet. Now, one important thing I do want to say, you don't actually use words. Like you don't use car, happy, because you have happy, happier, happiest, right? Happiness. All of them are related to happy. And so it would be impractical to have all of those words. Instead, you give it what are called subwords. And the subwords, the best analogy I can give you is syllables. So you actually give it happening. So ning, hap and nin. So that way, what's the value of that? That it can create its own words. Maybe it's never seen a version of happiest, but it knows happiest, right? It knows how to tack that on because it sees it in other examples. So you're giving it even that power. Okay? Okay, guys? So this is something that I wanted to, before I forgot, that the vocabulary is actually made up of syllables, if you will. It's not actually syllables because there's an algorithm that just calculates based on frequency subwords, but it's like syllables. Okay? Got it? All right, that's one important thing. Now let's switch gears. So the rest I leave to you guys, and let's just look at the code. Remember, as I said, instead of implementing an encoder and decoder for translation or just an encoder, we're gonna implement the more exciting thing, which is the GPT. A GPT is a decoder, okay? Just a decoder part. So let's go to the GitHub. Let's go to the GitHub. And I want to show you where I have this code so you can find it. And if you want to play with it during Thanksgiving or something, go ahead. Okay. So this works. So this will work. And it's exactly what we've discussed. And it's very much object oriented. Go to repositories. And then this one I don't have in the PyTorch because I was doing something else, but go to LLMs. LLMs just means large language models. All right, so you can click on that one. And then I have various things here related to LLMs, but the one you care about is from scratch. Okay, go to from scratch. And then in here, I have what is called the Tiny Shakespeare GPT from scratch example. So it's like a classic example for this. And I have that one in GPT, so you can go in there. And there you have it. This is a GPT. This is something that can generate language, okay? So it's basically this Python script, .py, generative transformer, tiny GPT, okay? And this input file is the training data. So if you look at it, if I click on it, it should basically be Shakespeare. Okay, so first citizen, before we proceed any further, hear me speak. Speak. And then let's see, where does it sound like Shakespeare? Doesn't sound very. Nay, okay, nay, but speak not maliciously. There you go. That's a good example of Shakespeare verse, right? Okay, so nay, but speak not maliciously. Notice also that this, interestingly, shows the author or the speaker, right? So it says speaker, colon, and it speaks. Other speaker, colon, and it speaks. You know, so there's some additional structure in there. Okay, so this is the training data. Now, let's just go over some ideas of this, and then obviously, probably next time we meet, we'll code this up, okay? So Tiny GPT, a Tiny GPT style LLM. This took me about 20 minutes training on my GPU. So if you're gonna do this on a CPU, be ready for an overnight kind of thing. I didn't actually do it, so I don't know on a CPU, but it'll take a while. If you have a GPU, then you're in luck. All right. GPT is only the decoder part of the original transformer architecture. So hopefully that's clear. That's definitely a question on the exam. So make sure you are clear on that one. The file in question is generative transformer tiny GPT. The tokens for this one, which is basically the subwords, right, are just letters. Okay, that's that whole alphabet that you see there is the entire vocabulary for this. Why can I get away with that? Because it's only like one text of Shakespeare. You see that? So there's not that much variety. If I was training as those chat GPTs are trained on the whole internet, then you have to have a much larger vocabulary. Number of tokens, Jason, right? So what are the tokens, right? So we get, so, but anyway, this is the vocabulary. So some symbols, letters, and uppercase and lowercase. Got it? And that's it. So this requires a thing called tip token. It's just a library that we're gonna use. Basically, this is what you do. So to find the vocabulary, you use libraries, sentence piece or BPE, tip token, and you just tell them what you want, and you give it. It's gonna run through all the text and give you the vocabulary, and then that's like one pass. Then once you have the vocabulary established, you do the second pass where you train the actual transformer architecture, whether a GPT or whatever it is. Got it? Okay. This is the training process as I did it. And you can see that the loss started at 4.2 and it made its way down to 1.4. So when you guys do this, it's not a homework, but just if you just choose to do so, hopefully you'll get the same results. Got it? All right. And then after that, I just, the tiny GPT model speaking Shakespeare. That's it. So this is a little bit of output of what it actually generates. So this is an AI, right? And you're just telling it, speak some Shakespeare. Okay. And so obviously I didn't give it that much data. I didn't train it for that long, but I think it captures some interesting things. one thing that surprised me is, notice that it picks up the speakers. So it creates a speaker and then the speaker speaks. And then it creates another speaker and they speak, and some speak more than others. You see that? So Sicinius, I don't know if it's making that up or if they exist in the thing. Menenius. All right. And then it speaks. So it says, such blessed upon by their hostess actions. Sounds very Shakespeare to me. I mean, does his crazy stuff though, right? It's not, this is what I want you to understand. GPTs initially they might start to sound very grammatical, but they're just making stuff. They're making things up. Okay. Then you do other things like you tie questions to what it's saying. And then there's human preference, feedback from human preferences, where you give it a question, it generates 3 outputs, and then a human every now and then says, this one's the best. And that feeds back. So there's a little bit of reinforcement learning, at least in ChatGPT. But that's an additional step later, okay? Or you fine tune it to a problem in particular. That, like question answering, that happens later. Right now, in this part, the pre-training part, you're just giving it all, the entire internet and all the books in the world, and it just learns to speak grammatically. And it learns to say that the knight was riding the horse. It's not going to learn the knight is riding the mountain, for instance. You know what I mean? It's like it learns correct things, but it can't right away answer questions. Okay, not necessarily, unless you gave it questions followed by answers. But when the way they usually train these is they give it all the text, all the books, everything, right? So it takes a long time. Got it? Is this making sense? All right, so we can take a look at a few more. What isn't indeed habit? I mean, that it's making up stuff, right? I pray you were the sword, man's so parted train. Okay, anyway, so that's the output of just letting it run. Okay, now you guys can try this if when we code this up, instead of training it with Shakespeare, give it Rick and Morty, what do you call it, transcripts. Maybe it'll start speaking like Rick and Morty, right? Or what's something else that might be very distinctive?
Big Bang Theory.
Okay, Big Bang Theory, right? Pinky and the Brain, Star Wars, it'll just start sounding like those things that it learned, okay? So that's the idea. All right, so we have a few minutes, 7 minutes left. So let's take a look at the code. And then, as I said, we're gonna code this up next week, but I just want to highlight a few of the things, right? So notice that it's our torch library as usual. So this is implemented in PyTorch. It's gonna have a whole bunch of variables now because we have to talk about the batch size. We have to talk about the embedding size, how many heads we want. And you guys know what I mean by that, right? So all of that is specified as parameters. Then this is just grabbing the input data. I got this from Andres Karpathy's repo. So he's got the tiny Shakespeare data there. All right. Length of the data in characters, right? So you can take a look at that. So it gives you the length of it, reading the whole thing. Then we have a few steps like figuring out the vocabulary. Okay, so we'll talk about that later, right, in detail. The tokenizer, okay? So notice here that you have the famous reverse dictionary and reverse dictionary. What that means is you have for a word, an integer, or for an integer, the word. This just makes it easy to find because it's a dictionary. In Python, it's a hash table, so it's fast. Okay, then you do the encoding and decoding of the IDs, right? And then, as I said, we'll talk about this later. Get batches, how we're going to read the batches. Notice that I do have the use of GPUs here. And then the calculation of the loss function, right? So we do have a loss function. And then notice here I have classes. Once again, we're back to object-oriented programming so that we can efficiently do this, right? So we're gonna have class, as I said, I will go over this code next time. And that will be the last thing probably that we're gonna do. But if you want, I do recommend that you start reading through it now just to help you out in your understanding. So I definitely recommend it. All right, so notice we got the head, right? That's got our familiar init, init function or familiar forward function. Then I have a multi-head attention class. You can see the same here. I got the feed forward classes. I got blocks, right? And this just allows me, so if you notice, a block is made up of what? Of feed forwards, multi-head attentions. You see that? So it just makes the coding where I have it in the book, it's not object-oriented, right? It's more like sequential, but it's longer. You saw how it was repeating things. Here, it's a little bit more efficient. So we got blocks, and the blocks put together multi-head attentions, feed forwards, and so on. Okay, then we have this class bigram language model, which is basically the class that should bring everything together. Okay. Here's the generate function for generating the text for the GPT. We instantiate the model. Here's the optimizer. This is the training process. And finally, once the model is trained, we're going to go ahead and generate text. So m.generate basically tells you how to start. Okay. In this case, see it, you just give it an ID, basically 0 to start generating things, where 0 is probably start of sentence. Got it? As I said, just really quickly today, please read through this code, read the 100 pages of the PDF. And then next week, hopefully that made sense. I know it's a lot. Look at the video again, probably. Next week, Thanksgiving, no class. And then we got 1 week of lectures. And we do have the competition. So the second half, and the competition only takes like a few minutes, really. So we'll do the competition, the homework for Sci-Fi 10, and then we'll go over this code, run it, and that's pretty much the end of the semester. Then we have maybe if I can squeeze in during the presentations a little bit of time, we might do MNIST with games. Okay, but that's it. All right. Okay, so hopefully that makes sense. I'm gonna stop the video here.